finite element analysis using SolidWorks. And in this video, we will be talking about fatigue analysis. In specific, we will be performing a fatigue analysis on a S hook, which we normally find on chains. Alright, so before we continue on with the video, let's just have a small discussion of all the content that we will be covering in this video. So the first one would be, we'll be talking about what is a fatigue analysis, and then we'll be talking about the different applications of fatigue analysis. After that, we will be discussing about the SN curve in fatigue analysis, and I'll also explain you what an endurance limit is. Then we'll just move on to the software part. We'll do a normal stress analysis of the S hook, and then we'll continue on to do a fatigue analysis of S hook, and then I'll explain you the difference between the 4 different types of fatigue analysis modules that are available in SolidWorks. And at the end of this video, we will be giving you a brief explanation about the different results that you can obtain by running a fatigue analysis. So let's move on. So the first topic that we are discussing is, what is a fatigue analysis? You see, fatigue analysis establishes whether your model is susceptible to fatigue damage when it is subjected to a varying load. But before we actually understand what fatigue analysis is, we need to be aware of two very important things. One is fatigue failure, and the other one is fatigue damage. So what are fatigue damage and fatigue failure? When components are subjected to loads which vary with time, they tend to fail at stresses well beyond their ultimate yield strength. This is known as fatigue failure. So why does fatigue failure even occur? It is due to the formation of microscopic cracks in the surface of the material. As we continue our cyclic loads, the crack continues to increase in its size. Once it reaches a certain length, it leads to fracture. This is actually well visible in this model, which I've actually showed to you in this screen. So here you have a normal shaft which has load acting on both the directions. We have a small crack here, and at one point of time it just experiences fracture. So how do we figure out whether a component will fail under fatigue? This is done by subjecting the model to a large number of constant amplitude cyclic loads and counting the number at which the fracture occurs. The test is then repeated to a large number of times with different applied stress values. We can plot the results into a graph, and this graph is called as the SN graph or the SN curve. The graph might actually seem a little bit overwhelming to many people in the beginning. It's not really that difficult. I'll just explain it to you. So here we have the SN curve for brittle aluminium with a certain grade, and you can see that in the y-axis we have the stress in megapascals, and in the x-axis we have the life cycles. So according to the graph, if the aluminium is subjected to 300 megapascals of stress, then the material will fail under fatigue stress with just 10 life cycles. The same way, if you subject it to around say 100 megapascals of stress, then the material will fail at around 10 to the power 6. That means around 1 million or 10 lakh life cycles. So using this curve, it allows us to calculate the number of cycles of load a material can experience before undergoing failure for a given range of stress. Fortunately, we don't need to perform the time-consuming tests yourself, as the data for these materials is published in many material handbooks and also many code books, and you can actually get the data online. The next point we will be discussing about is the endurance limit. You see, for some materials, especially ferrous metals, the SN curve becomes flat for lower stress values, and this is known as endurance limit. So what does this mean? Theoretically, the component or material can be cycled at this stress value for an infinite number of times, and it will never undergo fatigue failure. So for this material, let's say here we have the SN curve for steel, and here we have the SN curve for aluminium. We can notice that the SN curve of aluminium does not flat out, whereas the SN curve for steel starts to flat out at a stress value of around 30 ksi. So that means that 30 ksi of stress value, steel can theoretically endure almost infinite number of life cycles, and this is called as endurance limit. Now that we've actually had a brief discussion on fatigue failure, fatigue damage, and fatigue analysis, it is important that you also know a few applications of fatigue analysis. One of the most prominent ones is in spinal implants. When people have a few spinal impairments, like scoliosis, what they do is they perform surgery on the spine and they place spinal implants. Spinal implants do is they provide support for our spine. So whenever the person is going to bend over, the spinal implant will also bend over. And one way to ensure that fatigue failure does not happen in these spinal implants is by running a fatigue analysis. Another important application, analysis of power transmitting shafts. The next common one is turbine blades. This is the area where majority of the fatigue will take place in turbine blades. We could go into the particulars about it, but we are really constrained by time. Another one is airplane wings. If anybody who has traveled in airplane or at least seen an airplane take off or land, you would have noticed that every single time an aircraft lands, the entire wing structure, this area just moves up and down. Because of that, the place where the wings connect with the fuselage, this area, will actually undergo a lot of stress and also cyclic repeated stress. Because of that, fatigue can occur. Another one is athletic shoes. You would have noticed, right? Every single time we buy a new shoe, for the first a week or two, our shoe would feel like brand new. It would have this certain amount of resistance when we are walking. But as we continue to use the wear and tear, what happens? The specific area in our shoe begins to wear out because you're moving your. This is because of anatomy of our feet. Every single time we try to lift our foot up, only this area lifts up and this place is going to stay firm on the ground. Because of this, a lot of stress is being developed in this specific area of our foot, of our shoes. So what these big companies, big shoe companies like Adidas, Nike, Reebok, what they do is they run a fatigue analysis, and this is especially done for custom made shoes. So let's now move on to the software part of this course. Let me quickly go into the SolidWorks interface. All right, so I have opened SolidWorks. I'll just quickly go over and give Control O. So I've opened the S hook. It's a step file, so the software will be reading the model. You will also be provided the model. If at all you want to do this for your own practice, it will be linked below. Okay, we have our S hook here. So what we will be doing is we will be fixing this area, this place, and this part of our hook, and we will be running a small stress analysis with a certain amount of force acting in this way, and then we will run a fatigue study to determine how many cycles this S hook can experience before it undergoes failure. If you're still wondering where do we find this hex, just if you have a chain or any gold ornaments, you will be able to find the S hook. It's normally used to hold the two ends of our chain, and it helps us to remove it and put it back. This is fairly straightforward. All right, let me just go ahead and grab my SolidWorks simulation license. Okay, so now that it has come, let's go ahead and press new study. So before we actually move on with the fatigue study, it is actually important that we perform a static study or even a dynamic linear study, non-linear or non-linear study on this SO, because this is why we define the different parameters of our analysis. So I'll rename it as static hook and I'll click tick. We'll just continue to do the usual stuff. For material, let's go apply our material, apply edit material. Since this is a part of a gold chain, the material that we will be applying is pure gold. So for that, let's go to other metals and scroll down to pure gold and hit apply. And the color of our material has changed. Close. Now we will be fixing our model. So the parts that we will be fixing are this curve, this bend, this end, and this cylinder. Because we will be applying a force from here. If we fix this one, we won't really get any results from this. Let's press OK. And the external load will be, we will be applying force of Let's assume 200 newtons. Okay, just run this directly. Run this study. Don't really need to mesh it because this is a very small model. We can use the automatic mesh here. Okay, so the solver has seen excessive displacements. So it's going to change the type of solving. So it will be changing to large displacement model. So let's press yes. Okay, we have our results. As you can see, we have a 1 Mrs. stress. Most amount of the stress is induced in this area of our hook. And this is exactly what we needed. With this data, we can run a fatigue study. Alright, let's go to a new fatigue study. For that, right click, create new simulation study, and we will be renaming it as fatigue hook. And let's go and press fatigue. As you can see, once I press the fatigue simulation option, we again further get 4 more different fatigue models. So the first one is a constant amplitude fatigue analysis. The second one is variable amplitude. The third one is a harmonic fatigue study. And the last one is a random vibration fatigue study. So don't worry about all 4 of this. I'll just explain them with the help of an example. So let me just quickly go over and open my Jamboard. All right. So I have my Jamboard. For the exam, let's just take a normal cantilever as an example. Okay. So let me just draw here. So this side it is fixed, and we have the cantilever beam over here. Okay. And we have a force of, let's say, n newtons acting in this direction. Load versus time graph. So the load will be here as y direction. This is n, and the time will be t for seconds in this direction. So at 0 seconds, we don't have any load, and we'll just mark it as 1, 2, 3, 4, 5. So each one of these are actually 10 seconds. All right. So at 0 seconds, the amount of load that is acting on this cantilever beam is 0. Okay. And at 10 seconds, what happens is we decide to give a load of n newtons in this direction on this cantilever beam at this point. So what will the load be in this graph? It will be around here. And I'll just mark this as, just for the sake of reference, let's make this a small n. It will be small n, all right? And it will be acting downwards direction, so it will be a positive load. And again, at 20 seconds, the amount of load acting on the cantilever beam is removed. So at this instant, it will be 0. Let's mark it here. At 30 seconds, the amount of load that is acting on this cantilever beam will be n, but here's a small problem. We will be at here, the load will be acting in the opposite direction. To mark opposite direction, I'll just change the color here. It will be here, acting in this direction. Ensure that it's the same magnitude, so it's smaller, and that would be, since this is acting in a different direction, you will be considering that as a negative load, and that is at 30 seconds here. Again, the next another 10 seconds goes by, and the amount of load that is acting, it becomes 0. Now let's just plot all these graphs together. And now what happens is the same graph, the same pattern, it's followed again. What happens is the graph will look somewhat like this. And this is what constant amplitude fatigue loads are. At certain set intervals of time, you have a certain fixed value of load which is acting at a certain direction. with as the time progresses, the load remains constant, but the direction in which the load acts changes continuously with respect to time. So the next one is the variable amplitude history data. This we can explain by comparing it with constant amplitude. The only difference between a constant amplitude cycle and a variable amplitude is that here in constant amplitude, the amount of load and the time interval, everything is fixed. But in variable amplitude, just as the name suggests, every single parameter here varies with respect to time. So here you can see that at this specific time instant, n value of load is acting in the downwards direction. So we have a positive n value. And according to the graph, after a fixed interval of time, the direction in which n is acting will be reversed, but the magnitude will remain same. But that is not the case with variable amplitude fatigue tests. With time, the direction and also the value of the acting load will keep on changing. The next one is the harmonic fatigue study. The harmonic fatigue study is actually much similar to the constant amplitude study. In harmonic study, the loading and unloading will follow a sinusoidal graph. Let me just go to the workboard. So this is for a constant amplitude study. The graph for harmonic study will be somewhat similar to this. It will be a sine graph. That means it will follow the curvature of, most of you who have seen a sine graph or a cosine graph will be able to recognize this. This is how a harmonic study will be. So in a constant amplitude study, at 10 seconds for this example, we had n. Again at 30 seconds, we had n, but in the different direction. So it was either an extreme value in a certain direction or an extreme value in the opposite direction. But in a harmonic study, we will be gradually increasing the load here. So let's say from 0 to the maximum value, we're not going directly from 0 to 100. We are approaching it and we are increasing the value of load gradually. And again, in the same way, we're not decreasing the value immediately to 0. We are reducing the value gradually and again changing the direction of the load gradually. So that's the main difference between harmonic study and the constant amplitude study. And the last one is random vibrations. Random vibrations, this module is mostly used to run fatigue study for components which experience a lot of vibrations. This is pretty self-explanatory. So we will be performing a constant amplitude study in this. I'll just go ahead and press OK. Okay, so here we are in the fatigue analysis window. Before we start, let's just go check the properties. Here you can see the mean stress correction. Here you can choose between Goodman model, Gerber model, or the Soderberg model. For now, for this analysis, we're not going to select any of these because these are not required for such a simple analysis. We'll just press none and press OK. Right click on the loading and let's add the events. Here you can see that the static analysis that we have performed has already showed up here as an automatically selected. You can see that there are 4 different types of loading. They are fully reversed, zero based, loading ratio, fine cycle peaks. So the first one is the fully reversed loading. In fully reversed loading, the load value is fully reversed for a set number of cycles. So let's say we are having 1,000 newtons of force of load which is acting in a certain direction and it is oscillating between a positive and the negative directions. Essentially, what the software does here is that it changes the value of the load from positive side to negative for a single cycle, and the analysis is run for a set number of cycles. So in this case here we have set it as 1,000. So the load will be oscillating between a certain value. Let's say in this static analysis we have set our load as 200 newtons. So it will be 200 newtons for the first instant, and again it will become plus 200 minus 200, and it will continue on till we hit the required number of cycles. And the loading ratio for a fully reversed load is actually -1. The next one is the zero based. loading. In zero-based loading, the load is varied between 0 and the value of the load. So in the previous one, the fully reversed, what happens is that, so if our input load is around say 200 newtons as in our example, then the load will be oscillating between 200 minus 200 up until we reach the like total number of cycles, so here 1000. But in zero based, what happens is that it will initially be 200, again it will come back to 0, again it will go back to 200, again it will come back to 0. So this will continue on till it reaches 1000. And this is also actually called as the on off load, since we're for one instant we are actually giving load, and for another instant we are removing the load, so which is effectively just offing the component. So next one is actually loading ratio. Loading ratio is nothing but a ratio between the maximum to the minimum load that the component will be experiencing. So here in our example, we're giving say 200 newtons of load, and our loading ratio here, which is given by default, it is 0.5. That means that the load will be oscillating between 200 newtons to 100 newtons. So the maximum is 200, and 100 is actually 0.5 times of 200. So that means it is the minimum load will be 100. And in the same way, if your value is negative, then it means that the direction is also different from the initial value. So here 200 is our input value. Then if we have minus 0.5, then the minimum value will be minus 100 newtons. And the last one is find cycle peaks. Find cycle peaks is based on multiple reference studies. The program uses the stress results of the specified studies to find cycle peaks that give the highest alternating stress for each mesh node. An example of this would be if you are evaluating a scenario where a dead load is present. So in short, what this does is it will run multiple studies to identify the highest peak of the alternating stress among the studies that are mentioned by the user. And for now, we're not using any of these. We will be using the fully reversed one. And let's press OK. Our next task of action would be to add fatigue data to our model. So let's go and press the model and right click, apply or edit fatigue data. Once we press this, we have the material dialog box. Here you can see that the SN data is actually empty. So what we can do is we just go ahead and press the derive from material elastic curve. Initially it was fixed at define. That means the user will have to input the N and the S values manually, but we don't really want to do that. We will just press on derive from material elastic modulus, and the software will automatically generate one for us. We can either select based on austenitic steel curve or carbon steel curve. We'll select austenitic steel curves and press apply. If at all you wish to actually look at the SN curve, you have a small preview over here, or you can press on the view option here and it will open up a separate tab for it, where you can pan over and select and check all the values. Let's just close this one, hit apply and close. Now we have everything set up. Let's go and run the simulation. You just press run this study, and all right, we have the results. And the results are actually in two separate options. The first one is the damage analysis result, and the second one is for the life. Let's discuss about the damage. So the input parameters for us were we gave a 200 newtons of force in this direction on this face, and you can notice that this area has been completely damaged. This is from the legend. From the legend, we can see that this color associates with 100% damage. That means this part has failed for the fatigue study that we ran, and also the amount considering the amount of force that we gave. The next one is life. So in this option, we can actually check how many life cycles you can survive for. And this bend has absolutely failed, because here you can notice that the maximum number of life cycles this has survived is for 10 cycles. And after that, it has undergone fatigue damage or fatigue failure. So for 200 newtons, 1000 cycles, this has hook with cold material will not survive. And that's what we have concluded from this analysis. And if you're willing to practice this on your own, we'll be giving the model down below. You'll get a hyperlink to access the model. You'll get the step file. Your task, if at all you're willing to practice, would be to run a similar simulation, but with a much lesser amount of load. I gave 200 newtons of load. You can give 50, 100, 75 newtons of load, whichever load which you desire. And you can run this study and see how many cycles your S hook can survive. Well, that's it for this video, guys. Hope you've understood the concept. I'll meet you again in the next one. Bye.